We're very pleased to have Sam Keppard here who will tell us about demanding subgroups.
Yep, thanks to the organizers for inviting me. It's been a great series of conferences here in Montreal. Okay, so I'll start with the following question. How can we construct finite index subgroups of an amalgam of groups A and B over C? So one approach towards answering this question given by the following level. Suppose A prime is finite index normal in A and B prime finite index normal in B, such that A prime intersect C is equal to B prime intersect C, and I'll call this intersection C prime. There exists G prime, finite index in the whole group G, such that we can control the intersections with A and B. So G prime intersect A is A prime, G prime intersect B is B prime. So let's give a sketch for why this is true. And I'll do this by thinking about graphs of spaces and covers of graphs of spaces. Okay, so let's start with a space XA, a compact space with fundamental group A, and one for B, XB. And let's arrange it so that we have a subspace XC corresponding to the subgroup C, and an identical copy of this space inside XB. So that we can join XA and XB together by this kind of cylinder space XC cross with an interval. So this gives us overall a graph of spaces with fundamental group G. Okay, so how are we going to get this G prime? Well, we want to build a certain finite cover of this space. So how can we start? Well, we're given these finite index subgroups A prime and B prime. So these will correspond to finite covers of XA and XB. And we can then look at the pre-image of XC in these covers. It might have several components, which we call elevations of XC, and each of these components, let's say it's a space called XC prime. So this will correspond to the subgroup C prime in the lemma. And since A prime is normal in A, we know that each of these copies look the same because it's a regular cover of XA. And because of our assumption that A prime and B prime match up along the subgroup C, we know that we're going to have identical copies in XB prime. Therefore, we can join these together by cylinders as we did downstairs, and we get a map from everything upstairs to the space downstairs. Okay, but we're not quite done here because the number of copies of XC prime on the left might be different to the number of copies on the right. So here, for example, there's another XC prime on the left, which has nothing to match with on the right. So how do we deal with this? We can deal with this by having several copies of XA prime and several copies of XB prime. And we choose the number of copies carefully so that we can match up all of these green spaces. And now we're good. Now we've matched everything up. We have a genuine finite cover of the space downstairs, giving us this finite index subgroup G prime. And the way we've constructed it, it will satisfy the conclusion of the lemma that it intersects A and B in the right way. Not in this picture, but I think you could make it normal if you wanted to by passing to a normal core.
Where is the
So that we know that each of these copies, these green spaces, are all the same. Yeah. One could also prove this more algebraically, but I quite like thinking about it this way. I think it gives some insights on what the subgroup G prime looks like. Okay, so this then leads to the question, how do we get the hypotheses of this lemma? How can we come up with a good supply of these subgroups A prime, B prime, and C prime? What property of the pair AC, and similarly BC, what property would guarantee us a good supply of these A prime, B prime, C prime, as in the lemma? So one answer to this would be the following property of the pair A and C, that for any C prime finite index normal in C, there exists A prime finite index normal in A, which has the right intersection. A prime intersect C equals C prime. And similarly for BC. So if we had this property, it would mean we have free choice basically over this subgroup C prime, and we can always then find corresponding A prime and B prime that give the assumptions of the lemma. And then we can get this finite index subgroup as in the lemma. So we'd be able to get lots of finite index subgroups of G if we had this property. I will give some examples a bit later, so they will be coming. Okay, but maybe this property is a bit too strong. So we could also weaken this a little bit and still have a pretty good supply of A prime, B prime, and C prime. So for instance, we could replace this first part of the statement with the following. There exists C dot finite index in C, and then for all C prime finite index in C dots that is normal in C, you have the same conclusion. So this slightly weaker property is saying you don't have complete freedom over choosing C prime, but you're okay as long as you choose C prime to be a sort of sufficiently deep finite index subgroup of C, as long as it's sitting inside this C dot. So provided C has lots of finite index subgroups, this would still give us a good supply of C prime, A prime, and B prime that we can put into the lemma. So far, this is all looking at the case of a group amalgam. Of course, one could do the same game, but looking at a more complicated graph of groups. And this now takes us to the key definition of the talk about a group commanding a collection of subgroups. So a group A commands subgroups P1 up to Pn if there exists Pi dots finite index in the Pi, such that for all Pi prime finite index in Pi dot with Pi prime normal in Pi. No, I'm doing A instead of G. There exists A prime finite index normal in A that has the right intersections on the pi. So such for A prime intersect pi is equal to pi prime. Okay, so this is really the same condition as I was writing here, but instead of a single subgroup C, we now have a collection of subgroups P1 up to Pn. And we can independently choose these pi primes, and we get this single A prime finite index normal in the whole of A that has the desired intersections on each of these PIs. Okay. And the moral is the same as what we've been discussing with the case of amalgams, that if you have this property on vertex groups, then one can construct lots of finite index subgroups of the graph of groups. Yeah, it's really the same idea that this commanding assumption enables you to sort of match up these green spaces so that you can glue them together and make a finite cover. Let's also write down a slightly more concrete statement than this kind of moral, so we have something a bit more concrete to hold on to. So this will be a sufficient condition for G to be residually finite. So suppose G splits such that 1, each vertex group is residually finite. 2, each edge group is separable in its incident vertex groups. And then 3, the commanding hypothesis, that each vertex group commands its incident edge groups. Then G is residually finite. Yeah, so that's an example of something you can show using this commanding property. Yeah, I should also mention at this point, there's certainly no converse to this proposition. There are many other graphs of groups that are residually finite that do not have this commanding property. So there are other ways to show that graphs of groups are residually finite. This is just one situation where you get it quite easily. Yeah, one A prime that works for all of these PIs. Yeah. Well, in general, it's just very hard to construct these like finite covers of graphs of spaces. Yeah, you don't know that you would be able to fit everything together. Yeah, so it's not the only way to get residual finiteness, but commanding does actually give you much more than residual finiteness. It really gives you lots of control over this finite index subgroup. Sort of as we've seen with the case of the amalgam, it allows you to control how the finite index subgroup intersects the edge groups and vertex groups. So it's much stronger than residual finiteness. Okay, let's do some examples where we have this commanding property. Oh, and yeah, I should mention the terminology commanding is my own invention, but as we'll see from the examples, it's sort of something that exists in the literature already. Okay, so starting with an easy example, any virtually torsion-free or residually finite group commands any collection of finite subgroups. Yeah, the collection of subgroups will always be finite. Yeah, so this is easy to show. And in this case, you can take the pi dot to just be the trivial subgroup. Yeah, so in particular, if you have a graph of groups where the vertex groups are virtually torsion-free or residually finite, the edge groups are finite, then it's easy to construct lots of finite covers of graphs of groups. So, okay, maybe this is not so surprising, but it's still nice to have it fit in this framework. Next example, let's consider zk. This commands a collection of subgroups P1 to Pn if and only if the sum of P1 to Pn is a direct sum. Or if you prefer, you can say that P1 to Pn are linearly independent. So again, this is fairly easy to show. And in this case, you can take Pi dot to equal Pi. Okay, next example, a bit harder. This is due to y's. Any free group commands any independent collection of cyclic subgroups, where independent means that for the zk case, yeah.
Inside Z, take Z and do Z.
Yeah, you can't independently control how the intersections go there. Yeah.
So just for the sets of Z subgroups, this is the same saying that you're on this with respect to those.
Yes, you're ahead of me. I'll get to that in a second. Right, so independent means that a conjugate of Pi intersecting a Pj with I and J distinct will always be trivial. And this property of free groups is called omnipotence. So omnipotent means that the group commands every independent collection of cyclic subgroups. Yeah, so this is what we get for free groups. And Wise's motivation for this and for inventing the notion of omnipotence was similar to the motivation I've been giving in this talk. So Wise was studying graphs of groups with free vertex groups and cyclic edge groups. And he was classifying when these groups are subgroup separable. So of course, for this, you need to have lots of control over constructing finite covers of graphs of groups. So this is the property you want on the vertex groups. Okay, so there are a few other examples in the literature of omnipotent groups, but I will skip ahead in time a little bit to a much more general class of commanding groups. And this example will be a consequence of Wise's malnormal special quotient theorem. The example is as follows. Any virtually special hyperbolic group commands any almost malnormal collection of quasi-convex subgroups, where almost malnormal is kind of similar to independent, but it's slightly stronger. It means that whenever G, Pi, G inverse intersect Pj is infinite, it must be that I equals J and G is in Pi. So it's a bit stronger than independent because it also controls how how conjugates of the same Pi intersect each other. Yeah, so as you can see, this example is a very, very general, very powerful example. It holds for all virtually special hyperbolic groups. So for instance, many small cancellation groups, closed hyperbolic three-manifold groups. And also the allowed subgroups is far more general. It's not just looking at cyclic subgroups, but we can look at all quasi-convex subgroups, as long as the collection has this almost malnormality condition. And in fact, this can be made even more general using the relatively hyperbolic version of the malnormal special quotient theorem due to Teddy Einstein. If A is virtually special and hyperbolic relative to a collection of subgroups P1 up to Pn, then A commands P1 up to Pn. So this allows us to look at an even larger class of groups. For instance, a cusp hyperbolic manifold group will command the collection of the cusp subgroups. Sorry? If it's hyperbolic relative to your collection of quasi-convex subgroups, then yes. Yeah, I don't know if there's another more general statement you could get. Yeah, and this generalizes the previous one. So in the previous case, the group will be hyperbolic relative to the collection of the P1 to Pi as a result of almost malnormality. As a final example, there is a theorem from my PhD, which was published earlier this year, which again looks at virtually special groups, but now with no hyperbolicity assumption. So here we suppose that A acting on X is a virtually special cubulated group. So here X is the cat0 cube complex. Then A commands any independent collection of convex cyclic subgroups. So as you can see, this is very similar to omnipotence. The only difference is we require the subgroups to be convex, meaning that each subgroup stabilizes a convex subcomplex of X with compact quotient. Yeah. And this assumption really is necessary. For instance, if you take Z squared with the usual cubulation, and you take a collection of 3 independent subgroups, then it will not command them because you will have some linear dependence between these 3. But of course, in that case, they cannot all be convex. At most 2 cyclic subgroups of Z squared can be convex. Yeah, so you do need convex here. But one could certainly ask whether there is a more general statement that could be made here by looking at convex subgroups, but ones which are not cyclic. Can you get commanding of other collections of subgroups in this more general non-hyperbolic setting? Yeah, yeah. I think for one subgroup, it's not so difficult given the other things that you know about virtually special groups. Yeah. Does it? Although I guess suppose you do also want the normality of A prime in the whole of A, so maybe that makes it slightly harder. Yeah, I'm not sure. Okay, so for the rest of the talk, I want to give an application of commanding in another one of my papers. So I've actually used commanding in several different papers, but the theorem I want to talk about here is from my most recent paper, joint with Alex Margolis, Emily Stark, and Daniel Woodhouse. So again, G will split as a graph of groups. We will assume that 1, each vertex group is a closed hyperbolic 3-manifold group, and then 2, an assumption about the edge groups. Each vertex group, the collection of incident edge groups. Yeah, apologies, I'll have to go to this board. The collection of incident edge groups is an almost, or no, just is a malnormal collection of quasi-convex free subgroups, then any group quasi-isometric to G is in fact abstractly commensurable with G. Yeah, so this theorem, we have a certain graph of groups, and we show that it is quasi-isometrically rigid in this strong sense that for any finitely generated group quasi-isometric to it is actually abstractly commensurable with it. Okay, so let's give a sketch of what goes into this. So at least to give you some idea about where the commanding assumption comes in. So let's suppose we have G quasi-isometric to some mystery group G prime. And our goal is to show that G and G prime are abstractly commensurable. Right, so the first thing is to arrange for G and G prime to both act geometrically on the same space X. And this will be more than just a space. It will be a tree of spaces over a tree T, where T will be the Basset tree corresponding to the splitting of G that's implicit in the theorem. Yeah, so already there's a fair bit of work that goes into this. So in general, if you have two quasi-isometric groups, it's not true that you can get these groups to act geometrically on the same metric space. So we're really using the nice properties of the group G that we have in this case. And really it comes down to looking at the quasi-isometries from G to itself. And somehow the conditions that we have on the, how the graph of groups is made means that the quasi-isometries are not too wild. And from this, you can come up with a space. And also that the quasi-isometries preserve the splitting is another aspect of this.
Quasi-isometries of G would it be explicitly described?
Yeah, I'm not sure how good it is, whether you could explicitly describe it, but it's good enough to get the tree of spaces. Yeah, I don't remember exactly. Yeah, what we can say about the quasi-isometry group.
Could you explicitly describe the group of QIs of G?
But it preserves its problem.
Yeah, it preserves the splitting. So yeah, more or less it will come down to looking at the quasi-isometries of the vertex spaces. But I'm not sure exactly what the precise statement would be if you want to really understand what a quasi-isometry looks like. Okay, so let's suppose we have this action on the common tree of spaces. And this X will have certain properties that will come up a bit later in the sketch. Okay, so let's draw some pictures, or cartoon pictures at least. There, we have our tree of spaces X, and we want to consider the quotient of this by our groups G and G prime. So we're passing to finite index subgroups if necessary. We can assume that G and G prime act freely on X. And we can assume that X is simply connected. So this quotient is a compact graph of spaces with fundamental group G. And similarly, we get one for the quotient X mod G prime. So some graphs of spaces living downstairs here. Okay, so what we want to do now is construct a common finite cover of these graphs of spaces, as a common finite cover would correspond to isomorphic finite index subgroups of G and G prime, which is what we're trying to show. We're trying to show that G prime are abstractly commensurable. Okay, what color? Let's do orange. So let's consider one of the vertex groups upstairs and look at the corresponding vertex groups downstairs. The first thing is to get a common finite cover of these vertex spaces. Okay, so already we're using one of the additional properties of the space X here. And this uses that vertex groups of G are what's called graphically discrete. So yeah, this is a particular property enjoyed by closed hyperbolic three-manifold groups, I mean, among many other groups. Something specific we're using here. Yeah, so if you happen to be in Emily Stark's talk a number of weeks ago at the Geometry of Subgroups conference, then you'll have heard more about graphically discrete groups. There's yeah, a lot more that could be said here. But yeah, I won't say more about this in this talk, other than it's a property of the vertex groups which enables us to choose this X carefully in such a way that we can always get these common finite covers of pairs of vertex spaces. So let's just suppose that we have this ability. Yeah, so this tree of spaces X will be something combinatorial. It will be a combinatorial cell complex. Yeah, and in fact, if you look at the action of on one of the vertex spaces of the vertex groups of G and G prime, then these actions will already be commensurable. This is something you can arrange with graphical discreteness. So you can literally just intersect these vertex groups to get the finite cover. Okay, so let's look at now one of the edge spaces. See where it goes downstairs. Okay. And look at the next vertex space. And let's do the same thing and construct a common finite cover of these yellow vertex spaces. But now we also want to join these two together with an edge space that maps down to these edge spaces downstairs. So this is where commanding comes in. Okay, so let's look again at the assumptions we had in the theorem. The first one tells us that the vertex groups are closed hyperbolic three-manifold groups. Now these are known to be virtually special. So the second assumption means that, yes, we're in this case of commanding. Yep, so we are in a situation where vertex groups command incident edge groups, and using similar ideas to what we saw earlier in the talk, this enables us to carefully choose these vertex spaces such that they can be matched up along edge spaces, and we can actually glue in this edge space. Okay, so that's where commanding comes in. Right, so from here, we just repeat, getting more and more vertex spaces, which are finite covers of vertex spaces downstairs. And we end up with a tree of compact vertex spaces that covers the two spaces downstairs, X mod G and X mod G prime. Okay, so we're almost there. We want a common finite cover. Now we have a tree of spaces where each vertex space is a finite cover of vertex spaces downstairs. So the final step is to promote this to a common finite cover of X mod G and X mod G prime using a theorem called the graph of objects Layton's theorem. which was another result from my PhD. Yeah, so again, I won't say exactly what this theorem is, but it's exactly the right result to apply in this context, going from this tree of compact spaces, and these are combinatorial spaces. This is, you know, an important aspect here. So these are really just finite combinatorial cell complexes that we're dealing with. It enables us to promote this finite, tree of compact spaces to an actual finite cover of the spaces downstairs. Hence, G and G prime are abstractly commensurable. Thanks for listening.
So what's special about dimension 3?
Yeah, this would also work in higher dimensions, as long as you assume that the vertex groups are cubulated. So yeah, I just chose dimension 3, so I don't have to write this extra word. The cubulated comes for free in dimension 3. Yeah, this can also be weakened a little bit. So instead of 3 subgroups, you can take non-elementary quasi-convex subgroups that have cohomological codimension at least 2 in the vertex groups. Yeah, so that can be weakened. But again, it's a certain assumption that you need in order to have good control over the quasi-isometries. Yeah.
For splitting, you use the combinatorial assumption to control the splitting.
It's to control how wild the quasi-isometries are, where this assumption comes in. Yeah.
You didn't say anything about how you make your space. Can you say a little bit about that, your space F?
Yeah, so I suppose it goes in several steps. The first part is controlling the quasi-isometries to get an action on some metric space, and then we have to upgrade this metric space in order to make it combinatorial, and in order to use the graphical discreteness assumption. So the first space we get might have like too many symmetries on the vertex spaces. But using graphical discreteness, you can upgrade the space so that there are fewer symmetries on the vertex spaces, which is, you know, what you need to get the finite covers here. But yeah, there's quite a lot that goes into getting this tree of spaces exactly how we need for this common cover argument.
It's always true that you have a finite common cover of the vertex spaces down the space, like the associated, like, so you know you have to arm uncovering both of those arms.
Yeah.
You always get that.
The way we've carefully set up the tree of spaces, we get this. Yeah.
Right, so if you know there's 2 that like aren't actually commensurable, then you would know that that graph of groups wasn't quasi-isometric. Right.
Uh-huh.
More question.
One more thing.
I just want to ask if you can say a bit more about the graph of objects.
Uh-huh. Yeah, so one way of stating this is if you have 2 finite graphs of finite combinatorial cell complexes, and then a tree of spaces that covers them, such that the maps between vertex spaces are all isomorphisms. So here they're not isomorphisms, they're finite covers, but it's not too hard to reduce to the case where they're isomorphisms. And it's the case where they're isomorphisms, which is what the statement of the graph of objects latence theorem, where that comes in, and it gives you the common finite cover. Yeah, so I guess that the name objects is because the way I state it is in a fairly general sort of category theoretic sense, so that you can work in different categories of spaces, more or less. But yeah, that's all it is. It is just something where you're building common finite covers of graphs of spaces.
So is that sort of more general statement, like when you know the UI preserve the graph of full structure, you know graphical discretely, and then you know a commanding property that you have this form of rigidity or.
Yeah. Yeah, that's right. If you, yeah, carefully make sure that you have, yeah, all of the right assumptions, then such that the proof works, then you would get this rigidity, yeah.
And what we mean that for.